Throughout our universe, galaxies slam into each other at 270,000 miles per hour.
It'll completely rip everything to pieces.
It will even happen to our Milky Way someday.
If we want to understand galaxies, we're going to want to understand galaxy collisions.
Now, the most violent collisions in our universe when galaxies collide. Collisions. On a human scale, they're violent, leaving chaos and destruction in their wake. The bigger the collision, the greater the havoc. But once we leave Earth and head out into the universe and beyond, the scale of the collisions grows inconceivably. Galaxies smash into each other. Black holes fuse in a deadly fireworks display. Even our own galaxy marches toward a clash with its closest neighbor, Andromeda. These violent interactions, astronomers believe, spur on the evolution of our universe.
It's not just the gradual steady evolution that leads to the events that we see and that shapes the nature of the cosmos that we live in, but it's also the occasional violent collisions between two galaxies, between two black holes, between two stars.
In order for something to have gone right in our universe, things had to go very wrong.
How do we know of these violent collisions, and what do they mean for us here on Earth? Technology allows us to witness destruction beyond our wildest dreams, and to learn what these impacts do to the universe. Each type of galactic collision has expanded our understanding and changed our expectations of how the universe works. The largest collision imaginable occurs between the universe's most massive objects, galaxies. A galactic collision conjures images of unparalleled destruction. Stars collide, planets are shattered, all life forms are annihilated. But is this really what happens when galaxies collide? To begin to understand what a galactic collision means, we first have to understand the size and composition of a galaxy. A collection of gas, dust, planets, and stars. Lots of stars.
A galaxy is like a city of stars. It is a collection of a couple 100 billion stars that sticks together for billions of years. It's held together by its mutual collective gravity.
Our galaxy, the Milky Way galaxy, has around 100, 200 billion stars in it. And it's around 100,000 light years across from one edge of its disk to the other.
So we could cross the Milky Way by traveling 100,000 light years. No problem, right? Maybe we should start by measuring a single light year.
A light year is simply the distance that light can travel in a year. Light travels at an incredible speed, 300,000 kilometers a second. And if you multiply that by the number of seconds in a year, you get about 10 trillion kilometers. So the distances in astronomy are so huge that we actually have to use light years in order to measure the distances just between stars.
Another way of looking at this is that a beam of light traveling 186,000 miles per second would still take 100,000 years to travel from one end of our galaxy to the other. In the Sun's 4.5 billion years of life, it has orbited the center of the Milky Way a mere 20 times. Despite these great distances, objects within our universe collide all the time, as they have since the universe was young. Galaxies within the universe began forming hundreds of millions of years after the Big Bang, as clusters of stars and interstellar gas began coalescing due to gravity. These early galaxies were small, just 1/10 the size of the Milky Way.
The very first galaxies to have formed in the universe were small galaxies, dwarf galaxies. And as time went on, these small building blocks combined to make bigger and bigger galaxies as a result of mergers and accretion.
These dwarf galaxies found themselves, relatively speaking, caught in a traffic jam in the early universe.
In the past, the early history of our universe, interactions were much more common than they are today because galaxies were so much closer together.
As small galaxies collided, they combined into larger galaxies with defined shapes. The Milky Way galaxy, home to our solar system, is a spiral galaxy. Other shapes include elliptical galaxies and lenticular galaxies, a cross between the two. Astronomers owe these galaxy classifications to Edwin Hubble, the namesake for one of NASA's great observatories, the Hubble Space Telescope.
I think Hubble had a fun task, if you will, that there wasn't kind of a definitive, here's the classification system, so he got to make it up.
Hubble took on the astronomical task of categorizing galaxies.
What you look for is how to take care of 90%, to classify 90% of the objects there. And so you don't worry about all the strange ones.
What happened to the other 10%? Everything else went into the irregular category.
They're throwing off big tidal tails of debris, or there are galaxies that just look like a train wreck.
For years, that's where these peculiar formations sat. But the question still stood. What could have formed these strangely shaped galaxies? And could this have something to do with cosmic collisions?
It wasn't really a big topic at his time. I mean, just understanding spiral galaxies and elliptical galaxies was in its infancy.
Yet even as Hubble was more interested in sorting the majority of galaxies, he felt the ones labeled irregular warranted more attention.
It was roughly a couple decades after, when he did most of his work, that people started working and thinking about the irregular and peculiar galaxies.
Scientists wondered what made irregular galaxies look the way they did. One theory held that they were really snapshots of violent disruption and chaos.
There was kind of a debate, say 20, 30, 40 years ago, of whether these things were colliding and merging as we understand them now.
Today, astronomers continue to use this irregular category.
And irregular is kind of a catch-all term. It refers both to little galaxies that have been so disrupted by their star formation, punching holes in their gas, that their shape is very irregular. But it can also mean galaxies that have been very highly disrupted, for example, by collisions. It incorporates a wide variety of different types of galaxies.
The strange shapes of some irregular galaxies can be explained by the effects of gravity on a galactic scale. The largest objects in the universe merge in a head-on collision. Irregular galaxies are proof that these giant clusters of stars collide. They are the evidence that the universe is racked by destruction and pandemonium. But what happens within galaxies? What other types of collisions occur? And how can we see them? Irregularly shaped galaxies are evidence that galaxies collide. But do other celestial objects crash into each other? Our universe is both a nursery and a graveyard, host to an epic war between massive celestial bodies. Imagine this fictional scenario. Almost 3,000 light years from Earth, two sister stars have been sharing the same orbit for millions of years. Over time, they've grown closer, circling each other at nearly the speed of light. Then slam. In milliseconds, they are destroyed, sending out a shock wave that encompasses the Earth, decimating half our ozone layer and killing everything in its path. This is what some astrophysicists theorize will happen if a type of star called a neutron star collided near Earth. For astrophysicists, 3,000 light years is near.
There has been a suggestion that one or more of the mass extinctions that happened to life on Earth occurred because of such an event.
Some of the most violent stellar collisions occur between neutron stars. Neutron stars are born of remnants of older giant stars that have run out of fuel.
Gravity causes the whole thing to collapse. In the center, an extremely dense object forms. It's so dense that the electrons get pushed into the protons to make neutrons. The neutron star that forms at the center is the remnant, the ashes of that star.
But these ashes have some life in them, and after their creation, some neutron stars orbit each other in a gravitational embrace called a binary pair. For millions of years, the stellar siblings orbit each other up to 1,000 times each second.
They will be emitting gravitational waves which drain away energy from the system, getting them closer and closer and closer together until ultimately they get so close together that there's no more stable orbit for them to orbit on.
When they finally collide, they release more energy than our sun would produce in its lifetime. Yet the collisions are too fast for telescopes to capture.
For neutron stars, the whole collision is over in about 1,000th of a second. Then it's done. Once they touch, they go splat, you're done.
Their collision sends a massive shock wave through space. From Earth, the collision is detected as a short gamma-ray burst, or GRB. A GRB is a short-lived yet powerful event, evidence of one of the most violent collisions in the universe. But scientists have only recently begun to fully understand what GRBs mean.
There are little gamma ray flashes that happen a couple times a day in the sky. And we pretty much monitor the whole sky for gamma rays all the time. And these have been known for about 40 years now.
The U.S. Air Force had actually detected GRBs years before the scientific community even knew they existed.
Gamma ray bursts were discovered completely by accident by military satellites and came as a result of the Test Ban Treaty in the 1950s under Dwight Eisenhower.
The nuclear test ban treaty begun under President Eisenhower resulted in the creation of military satellites designed to search for nuclear explosions. The Air Force launched the first Vela satellites in 1963. This series of satellites was built to detect, among other things, gamma rays, using gamma ray detectors.
The clouds of radiation that would be released in such an explosion would be releasing gamma rays. Those gamma ray detectors were the first ones to detect cosmic gamma ray bursts.
In 1969, Ray Klebesattel, an Air Force analyst, found strange spikes in gamma rays within the Vela data that, because of their intensity and duration, could not be attributed to either the Earth or the Sun.
So they knew they must be coming from somewhere out there.
By 1973, when Klebesattel finally made his research public at an American Astronomical Society meeting, he had at least 16 confirmed gamma ray bursts. But more sophisticated equipment would be needed to fully observe GRBs. In 1991, NASA launched the Compton Gamma Ray Observatory, a space satellite dedicated to detecting GRBs. What scientists hoped to do was catch a gamma ray burst in action in order to determine what it was. Could GRBs be a type of cosmic collision?
The Compton Gamma Ray Observatory detected a couple of thousand of these gamma ray bursts and established that they do in fact happen all the time. But what was really needed is a way to quickly identify the gamma ray burst and quickly get a telescope on there to take a picture, because they fade away quick.
In fact, GRBs fade completely away within just a few days.
5, 4, 3, 2, 1, have ignition, and we have liftoff of NASA's SWIFT spacecraft on a mission to study and understand gamma ray bursts throughout the universe.
In 2004, NASA launched the aptly named SWIFT telescope to better track and react to GRBs.
SWIFT is a satellite with a big gamma ray detector that is relatively good at detecting the direction from which the gamma rays are coming. As soon as it sees a gamma ray flash, it radios the location to the ground, and then it starts swiveling an X-ray telescope to that same location.
In 2005, SWIFT detected a burst, and in less than a minute, it repositioned itself to observe its afterglow. Meanwhile, SWIFT sent the GRB's coordinates to its network of ground telescopes. One of those telescopes is located near the summit of Palomar Mountain in San Diego, California. The Palomar Observatory combined its data with calculations from more than a dozen other institutions. Together, they were able to identify a probable cause of the short GRB, a collision between neutron stars. Since stellar collisions occur within a second to a few hours, most of what happens remains a mystery.
The actual collision event is a very short-lived thing. It's for that reason that it's unlikely we'll ever in our lifetimes be able to capture a couple stars in the process of colliding. But what you can do is you can look at the aftermath.
So, while astronomers have never actually witnessed a stellar collision, they know they exist by examining the ruins of these brutal star wars. Neutron stars are not the only stars that collide in violence and destruction. Even infant stars can create cosmic havoc. Stars lead a violent existence, and not just neutron binary pairs, but virtually all stars, starting with the nature of their formation. The turbulent life of a star begins with the death of a molecular cloud.
It's a dense region of interstellar gas. In these clouds, stars form, planets form, our own solar system formed.
Molecular clouds grow larger as the force of gravity from them attracts more gas and particles until their density gets so large they collapse to form stars. An exterior force like those caused by a cloud collision or the shock waves of a supernova can also cause the clouds to collapse.
As it collapses, it gets denser and denser in its center. It gets hotter and hotter in its center.
Recent research places the first star formation at only 100 million years after the Big Bang. Some of those stars, astronomers believe, can still be found in our own Milky Way galaxy. Today, researchers focus on compact groups of stars called globular clusters. For those researchers studying stellar collisions, globular clusters are the place to look. These dense collections of stars serve as an ideal stellar battlefield.
Just like if you're walking down a street in a crowded city, you bump into people. And stars are close enough together and they're crowded enough, they bump into each other.
With about 100 billion galaxies in the universe, and with each one containing about 30 globular clusters, the number of stellar collisions can be staggering.
If you count up all the galaxies in the universe, hundreds and hundreds of billions of galaxies, and ask how many regions do they have where stellar collisions could occur, it starts to be a very large number.
It was a mystery within globular clusters that led astronomers to one of their biggest discoveries. Discovered in 1953, highly luminous stars in globular clusters stumped researchers for more than 40 years. They named the strange stars blue stragglers.
These blue stragglers have some peculiar characteristics to them. They're called stragglers because, unlike other stars of the same mass in that cluster, they haven't yet gone on to later stages of evolution. So they're stragglers and they're blue because they're hotter than the other main sequence stars in the cluster.
It seemed blue stragglers had discovered the stellar fountain of youth. Scientists wondered how that could be possible. NASA's Hubble Space Telescope, launched into orbit in 1990, played a key role in answering that question.
Hubble's resolution is so fantastic that if you could look with it from New York